Okay, I think we're good to go. We'll test and hopefully make it stay live. For those of you remote, we now have the first speaker of tonight, Aram, who is going to speak about QLang, interesting topic. And then we're going to have 2 other talks. If you're just tuning in, this is a meetup.com meetup. We'll provide more information in the description. And for all of you here, thanks for the patience, and we'll finally get started. Thank you.
Hello, I'm Aram Hăvărneanu. I've been a gopher for 13 years now, I think, and more recently I've been working on Q, which is a configuration language I find really interesting, and I hope that after this talk you will find it also interesting. So first we're going to look at what exactly is configuration, more importantly what kind of problem we're trying to solve over here, and we'll do that by looking through history. We'll do a walk through history and see how the computing landscape changed, starting from the very beginning, actually, up to the cloud era of today. Then we're going to do like a very basic tutorial on Q to see how the language looks like and behaves. And then we're going to see how Q can be used to solve problems that you might have today with the cloud, say like using Kubernetes or whatever else you're doing in the cloud. And by the way, this is a talk about Q, not about history. So there might be, if there's any historical inaccuracies, I'm sorry about that. I'm just trying to kind of see how the computing landscape changed over time to where we are today. So we intuitively know what configuration is, but let's try diving it a little bit deeper on what it means, because configuration is obviously a subset of data, but it's more specific and has more interesting properties than just that. So let's discover the properties by starting from the very beginning, the early days of computing. This is by some considered the first programmable computer, and as you can imagine, many computers of that era had cables like that, but the cables in this one are more significant because by moving those cables in the patch panels, that was how you actually program the computer. So in a sense, it was not programming the way we expect it today, like we didn't have any languages or anything like that. It was more like kind of hard coding an FPGA to do a specific job. And as you can imagine, that's extremely difficult. Yeah, so programming was very difficult back then, and this computer was used for ballistic calculation. So somebody had to enter the data into the computer, and they used punch cards, which we'll look about in just a moment. But the idea is that we already had ways of generating this data, and it was relatively easy, just existing technology of the time, to put the data in the computer. But programming the computer was extremely difficult. A few years later, we had this computers like this one, like the IBM 704, which is historically significant because they invented Fortran and Lisp on this computer, and they used punch cards, which look like that. Each one can keep just a line of text, basically, and they are stacked like this. People scribe notes on them to remember what they are and parts of the program. And like the previous computer, you had to put the program in the computer somehow, in this case using the deck of cards, and then you also had to put a deck of data in the computer. So we see that programming became a little bit easier because at least now we have languages and we can write sort of like programs. Data, it's still the same way that we dealt with data. So back then, programming, and for a very long time, programming meant doing something to the machine. In the early days, doing something physical to the machine, to make the machine do something useful for us, to solve a useful problem. At some point, we invented hierarchical file systems. Of course, Unix became dominant, and we recognize this from like a Unix file system tree. But there's something significant changed at this point. Computers became interactive, and data became sort of like ambient, like some sort of ambient universe around the programs. So programs were not necessarily tied to their data as before. Like before, we only used computers to solve one particular problem at the time, and each program had to come with its own data. This was very tightly coupled. But nowadays, we can kind of manage the data in the program separately. So in the case of Unix, for example, we can just use tools like copy and move to just move data around and do operations with data, because at least in Unix, files are just byte streams, so we don't have to worry about the interpretation of the data inside the file. That's up to the program, and we can manipulate data independently of the program in a specific sense. And we try to make our lives easier by having this separation. And basically by then, I think it's because we had interactive computing. Programming became somewhat simpler, and because of that, we can afford to try to do more. So we have a world where data and code are forever separated, and we're not only solving a particular problem when we're programming. Rather, we're trying to write programs that solve a larger class, a general class of problems, sort of like a problem factories. Rather, the output of the program is like a solution factory. So programs became more general and bigger, and of course, it's more difficult to deal with bigger and more complex programs. So we had to invent all kinds of things to deal with this complexity, and we developed all kinds of programming techniques and that we use today. And I won't read these all. And in fact, it doesn't matter what it's written on this slide. This is just a brain dump that I had when I created this slide, and I could have put twice as many things, but it just stopped because it was becoming too small. And I think that you can put here your favorite things about modern programming today that you think are important, and they make your life easier, and they help you writing more complex problem or deal with complexity in some way. So over the 70 years or whatever we had computing, maybe even more, we had to invent all this technology to basically deal with like the billion-line code bases and million-line programs that we have today. And it's a lot of stuff, as you can see over here. But as we talked before, programs and data become distinct. So what happened on the data front? Well, actually, a lot of things also happened on the data front. We invented databases of different kinds. We invented relational databases which have useful properties like ACID. We discovered the CAP theorem. We discovered error correction, which is absolutely useful and critical for things like RAID and things like that, which eventually led to planet-scale database systems like Google Spanner and other similar systems. So interestingly enough, there's fewer things on this slide than on the previous slide, but in some way they're more fundamental, because whereas we can debate whether functional programming or object-oriented programming is better or whatever, people kind of agree that ACID is a good property to have, and the CAP theorem is just pure math. So in a way, there are fewer things that we seem to advance in data, but what we did is it's more fundamental. And I think that's because in some way data is simpler. It's sort of like more static as opposed to the code where a program and its instance are very different things, because an instance has like an internal state. So we definitely did lots of advancements dealing with data. But what about configuration? Well, as we said in the beginning, configuration is a subset of data, but what is it that's more than that? And coming back to the time where we started writing programs that can solve like a larger class of problems, we use configuration as a way to control the programs. And we still do that today. I mean, Nginx and whatever daemon you're using has a configuration file that specifies like properties. Like, for example, we want to listen to a single Ethernet interface or something like that. So configuration is a mean of control. And up to very recently, it pretty much meant controlling the computer or the operating system. But nowadays, of course, it means controlling the cloud. Programming used to mean that we did something to the machine to make the machine do something useful. But now it means that configuration is about doing something to the cloud to make the cloud do something useful for us. And I quite like the metaphor of the cloud. I mean, what is the cloud? I mean, cloud is just someone else's computer. But when I say cloud, of course, I mean systems in the cloud. But I really like the metaphor of cloud because it kind of makes it sound like it's a black box. And it is in some sense, because if you're working in the cloud, of course, you have like an area of visibility around you and can poke inside the cloud or whatever cloud system you're doing. But at some point, there's a horizon over which you cannot or do not want to look, and you're just treating the rest of the system as a black box. And in some case, it can be like a hard limit that you cannot go through. For example, if you're dealing with a proprietary system like AWS, you don't know what's going on the other side. So you have to treat this stuff as a black box. So I quite like this metaphor of the cloud, and what we're doing nowadays is the way we engineer systems that work in the cloud is by doing lots of configuration. For example, if I create a system, I have to configure that Docker containers run inside Kubernetes, and that's all configuration. And that's all configuration. In some sense, configuration at large scale took the place of what we used to do programming, engineering-wise. So configuration in this particular sense, it's kind of similar to programming. So, and it, of course, seems to be quite important thing. So are we well prepared on a technological or theoretical level to deal with configuration? So what's the state of configuration today? Well, it's this. Pretty much all of it. That's it. We have other things that are quite similar to JSON, XML, and YAML, but semantically they're quite similar. I mean, they're just representations for very flat data with very little intrinsic semantic and very little power that they can do. And I first of all, we can ask the question: Is this a good place to be in? Because we had this thing before. Now, first of all, I don't even think that most of this stuff is necessarily good, but it's definitely been essential in being able to achieve complex systems, the complex systems that we do today. So can we do this only with this? And of course, in fact, it's even less than this, because we don't want XML generally, and it's not necessarily used that much in the cloud. It's mostly JSON and YAML, and people are kind of converging on YAML. So it's really only this. Is this good enough for our cloud configuration needs? And I don't think it is. I think we're kind of missing like a lot of advancement, especially on the theory side, because what happens when we interact with the cloud, essentially there's some sort of internal protocol that happens there. You communicate messages back and forth. Doesn't matter whether it's RPC or REST or whatever it is. There's sort of an internal language that's specific to every system and every pair of systems that the two systems have to agree on what it means. So there's sort of like a DSL that's per pair specific, but we don't see it. Like there's no syntax for it or anything. We don't even know necessarily what it is, because how we use it is by embedding this DSL into super flat things with no internal structure, like for example JSON and YAML. So instead of, to make an analogy, it's like we're speaking English here, but the level of we cannot express the fact that we're speaking English, but what we say, everybody is using the Latin alphabet. I mean, yeah, that's useful, but it's not enough. So I think we're kind of in the Stone Age here. We're using this language because when we embed them, we lose the useful properties that this internal language naturally have. For example, they come for complex systems where data has all kinds of internal references and cycles, and then creates a complex topology and all kinds of constraints which are very meaningful. But we cannot express any of this stuff when we convert it to JSON. We lose too much stuff. So of course, I think that Q is an attempt to fix this problem. It's definitely not the only one, but it's the one that I'm going to talk about today, because I think it's pretty simple and pretty interesting. So the Q language is very simple. So we're going to start with, of course, only with hello world. And this is hello world, but we can do more interesting things. For example, we also have import statements. We can import packages. We have comments, which some configuration languages lack. And we can pass things around. For example, the small hi, we pass it to the toUpper function, and then we also call the length function on the string itself. And if we try to run it, of course, we get the original string, the string in capitals, and the length of the string. So there seems to be some sort of power there already. But of course, what you see on the right-hand side is basically native Q output. So that's on the left-hand side is input, basically the program, if you want to call it the program. On the right-hand side is the output of the program. But Q supports natively all kinds of outputs, not just native Q. It also supports JSON output, and this is absolutely essential to Q. It's basically a polyglot universe. Not only it can export to other languages, but it can import and reason about data coming from other languages, like JSON and YAML. So this is an absolutely first-class citizen in the Q ecosystem. That when you evaluate the Q program, you can get, for example, in this case, JSON, or in this case, it's YAML, which kind of looks similar to the first example. Q has more power. It has arithmetic. It's actually arbitrary precision arithmetic. Again, we can call functions. We have pi and things. If you look at Z over there, you can see that Z references X and Y, which are declared above. So that's a true reference. There's no like converting to string or just being a copy or thing. It's the actual thing that we have previously declared. Again, which is something that you cannot do in many other configuration languages. And everything that you see on the screen is a declaration. It's not like an assignment or things like that, which will become more important in just a moment. We also have lists. If we declare 4 things, we can put them in a list. We can add more other things to it, and then we get, for example, this output. And when we compile the list, for example, to JSON, we get an array. When we compile them to YAML, we get this sort of thing. I'm not sure how they call it in YAML. We have structs, which are a way to organize and combine data, which of course you would expect in pretty much every language. What's interesting about this one, though, is that if you look at the population of Vienna, we have prefixes, so it's quite easy to specify numbers and things like that. And we can use the Vienna and Salzburg declarations into another thing. We put it into a bigger struct, Austria, where we put the reference to the capital and also put a reference to the cities inside there. And again, it's not a copy; it's a true reference. And when we compile that to YAML, we get basically this. So you can imagine how that works. Now, so far you've seen just basically values, like sort of the things you could do in many other languages. For example, YAML. Like here we said the population is a number, or we said that the name of something is a string. So basically, we just declared that something is a very specific value. But Q it has more interesting properties, because in Q, types are values. Or another way of saying it is that Q values are can be types. So what's on the left of the column is basically a value, and what's on the right of the column is also a value. So in this example, we declare that X is an int, and we also declare that S is a string. But we can also, of course, have much more interesting types. We can say that IP is a net IPv4, so it's a specific IP. It's not just like a string, and we can see that in action over here. For example, we have previously said that X is an int and S is a string, but we can also say that X is 100, which is a very specific int, and S is hello Vienna. And what happens here is you shouldn't think of this as the first one, the first things there as being like type declarations, and the second one like being assignments. That's not what's happening. All of them are declarations, and a declaration in Q means basically you say is. So you say X is an int, or you can also say X is 100. And we can say that IP is an IPv4, and you can also say that IP is that particular IP. And the interesting part about that is that if you put the wrong IP, if you put like a string which is not a real IP, Q will complain and will not let you do that, which is of course very useful. And we will look a little bit later how exactly does it do that. But one thing that's important to think about, like conceptually, if you want to think about these things, is that Q values are sets, like mathematical sets. And sets can be large, big, infinitely large, or they can have a single element. And for example, int there in the first declaration is basically an assertion. We say something about X, and in the int, it means that of course it's an infinite set. But if you look at X 100, that's basically one element set that only contains 100 plus button. Well, we won't go into that. Going further, we can be more precise about types. We don't necessarily have to say that X is an int. We can also say that X is less than 10. And then if you try to say that X is 5, that works fine because 5 is less than 10. But if you try to say that X is 12 again, Q will complain, which is again very useful. So we can refine types. And basically every declaration, what happens here is that every declaration can make the value only more specific. There's no way to make it more general. There's no way to change anything because every declaration just asserts something that is true about the value. So we assert that is an int, we assert that it's less than 10, we try to assert that it's 12, and we fail. So everything things can only get more and more specific, and there's like an implicit end, logical end between everything on the top level. There's no ordering or anything like that. It's just a logical end. And by the way, if we do something like this, the difference between this example and this example is that here less than 10, if you want to think about it in terms of a type, it's sort of like an anonymous type. It doesn't have any name, but of course we can give it a name. So in this case, we create a range, something that's between 0 and 10, which being an int, it only has 11 elements. But then being a Q value, we can just say that n is a range or is part of range. So we can essentially create a new type this way. And of course, 8 is in that range. Another interesting thing is that if you look at the Q output, it actually simplified our input. We had those 3 lines. Now it actually combined the greater than 0 with int. And it says just it's a uint, like an unsigned int. You know how to do that. And it replaced the 3 lines with a single line. And the implicit end that we had between all these declarations has been replaced by an explicit end over here. And of course, you can do that ourselves. We have end, and that's very important in Q. We have this logical end. And the way it works is sort of like this. If you look at we try to declare a city, and we try to declare a city by doing the end of essentially 2 anonymous structs. The first one has a name and the population, and the second one has only the elevation. But what happens really is that whatever city is, it has to have all these properties. So the first one and the second one, so the output is basically we add a field. We add fields this way, so we can add more fields to things. Yes. Then having defined basically a specification, so city, you can think of it sort of like a specification for what a city can be. We might want to write a specific example of a city. Coming back to Vienna here, we say that Vienna is a city and all this other stuff, which fits the specification, like name, Wien is obviously a string. We can add more stuff, so we're not specifically limited to the specification, except for closeness, but we won't get into that. So in general, it's possible to add more things. If you look at elevation, previously we said that elevation is 190 meters, but we do not have to be concrete. Actually, maybe I only know that the elevation of Vienna is between 151 and 542. So that works also because this range is also part of the number. It is a subset of number, basically. So this works. You do not necessarily have to be concrete and get a single value. And works also on lists. It works point-wise, basically element by element. If we have and, you might think about, okay, but do we have or? Yes, of course, we have or. I'm not going to go super in detail about or because it's slightly more complicated and you have to think about things because it's not slightly less intuitive. But for example, if you look at the inverted range, it's kind of like the interval we had before between 0 and 10, except now it's the outside part of it. And we can try up some numbers n0 and n1 to see if they are indeed part of that range that we declared. But if you try 5, it doesn't work. And again, to clarify another point, there's n0 and n1 over there because they're 2 different things. You cannot change one thing is fixed. There's no mutation or anything like that. We can also, so or is an exclusive or. So for example, if I want to make up a list of things which are both either persons or companies, of course, a person has a name, a company also has a name, but a person might have a mother, company certainly doesn't have a mother, but it must have something like a tax ID. So when we declare a legal person over there, we're saying it's one of those two things. So it's a disjunctive or, and then we can declare things like that. I'm not going into very much detail into this because we're not going to show selectors into this anyway. But the idea is that these logical operators form an algebra which ensure that Q is compositional and very easy to reason about. And compositionality also gives us scalability and allows us to combine sources of data from different places and be sure that it kind of works the way we expect, and it's all simple and things like that. We did look a little bit at functions because we called functions before, but let's look at them a bit again. For example, in this example, I have this album which was released in 1989, but then again, the way I just wrote it here, you can put anything in the release. You don't necessarily have to put the date, and we don't want that. We want to make this example type safe. We want to make sure that whatever you put in the release label, it's a valid date. And the way we do this is basically like this. So we have a specification for the album where for release, we say that release is a string, and also release is or conforms to this specific format over here. And time format, by the way, is the Go time format. So that's why it looks like that. So in this particular case, if you try to put something else inside release, it wouldn't work because it wouldn't conform to the format. So in a way, you can use functions of this sort, so like predicates that kind of tell you if something is in a type or not, which is very useful. Now, the main important part of Q and the most interesting part of Q is the comprehensions. We're not going to go into a lot of detail here, but basically comprehension. So Q values without comprehensions, Q values form like a topological structures because things can refer to other things. What comprehension, so they have a shape. If you don't like the word topology, they have a shape. Things have a shape. What comprehensions allow us to do is take that shape into account and generate a new shape. So the input to this thing is we want to reason about the shape itself, not necessarily about the values there, but we can definitely use the values. So what happens here, for example, essentially we can kind of generate new types. So we have a list of labels 1 to 3. By the way, the underscore only means that it's kind of like a private, it's kind of like a lowercase identifier in Go. So it doesn't go, it's like it doesn't go in the output. You don't see it in the output. But other than that, it doesn't do anything special. So we have a list of labels, and we iterate through the labels, and we create a struct where the keys are actually the values that were in the labels. But the value of the key is that thing. So we convert the string representation to an integer, and then we just multiply it by 2 because why not? So we can create new shapes out of old shapes, and that is incredibly useful. A more complex example here, you don't have to understand this, but what really happens is like it's U and V are, you can think of them like two vectors, and this is basically the way to compute their outer product. Doesn't matter the specifics. The only thing that matters is that you can do that. You can take like a one-dimensional object like a vector, but you can create a two-dimensional object, essentially like a matrix, which is basically a list of lists. Now, if that is all comprehensions can do, it wouldn't be that impressive, I don't think. Another thing that they can do is because the way I just explained them, you can have like sort of like a universal quantification over something. But it can be more specific than that. For example, in this case, V ranges over the list of numbers, but we are only interested in the positive numbers. So we can have the if over there that checks that V is greater than 0, and then only then take it into account. So basically, we have the original list of numbers. We generate this way a new list of numbers called naturals. You can see over here are only the positive ones, and then down there we compute their sum. Now, just for fun, a more complicated example here. We just have the fruit structs with labels 1 to 3 and values apple, pear, and cucumber. We can generate this other struct where we basically invert the keys and the values, and for the values we just double them. So what we see here is that string interpolation. If you look over there at V, colon K and K, we can get the string representation for K as a string, and we can put it in a string. So we have string interpolation, which again comes very useful. Now this was just very basic and very quick tutorial on Q. So there are many things missing. For example, we have ways to specify defaults value, which come very useful when you try to create something like a template. We have optional fields, closed values where you cannot add things to structs, embedding, which kind of works like Go, struct embedding. We can use regular expressions for predicates. We have a package system, and there's lots of tooling. Like there's the tooling layer can do all kinds of things. For example, everything that I just showed before this is pure. There are no side effects. It's all safe. You can always try to evaluate Q that way. But there are ways of actually doing effectful operation from Q itself, but it's an opt-in thing. So you have to explicitly want to do it. And there's a Go library that can help you do things. And for example, if you get an input in a server, like your RPC server or something, you don't want to call for the command line to validate your data. You just want to use the native Go library. So there's lots of stuff going on here. So how can that how is that relevant to the cloud? Well, I kind of said that Q integrates with the cloud, but what I really want to say is that Q integrates with your cloud, whatever it is, because Q can reuse and use your existing configuration in any language. Well, not quite any language, but at least it's like JSON or YAML. It can use that, and again, the output of Q can be also those languages. So basically, there's no cost in just trying out Q, because you don't have to change your infrastructure at all. You can just try it, and it can be like the invisible guardian angel that just takes care of the consistency of your infrastructure. But how does it do that? Well, it does that by I didn't go very far into the mathematical theory behind Q. You can read more about that. It's based on lattices, but it's compositional, and it's extremely powerful. And most importantly, it can express the ad hoc protocols or DSLs that already exist in your infrastructure, but are just flattened out to JSON nowadays. You can actually semantically reason about those things in Q itself, and that can help with all kinds of things, like it can decouple services, because you know exactly what's the important part, and you can ensure that part doesn't change. Put more guarantees into things, but all in all, it just makes system more robust to change, because fundamentally what it can do is that you can actually test configuration changes before deployment. Like nowadays with Kubernetes, you might have to wait 20 minutes in some test environment, and maybe it works, but there's not real testing. It's just trying some things out. But this, you can exhaustively check your config mathematically before trying to deploy to see if it conforms to whatever specification you want to do. So if any of this was interesting to you, just some notes about the Q, the Go community. Yes, of course, that's our website, qlang.org. Which has documentation and all kinds of guides and things like that. Also the spec, which is quite readable, just like a Go spec. But there's another third-party site from somebody from the community wrote. It's tutorials.com. It's excellent tutorials, excellent Q tutorials, and I really recommend take a look of that. And it kind of speaks to our community that we have people who invested so much that they created these resources essentially for everybody, which is absolutely great. And if you want to keep in touch, of course, we have a Slack. I didn't put a link in here. I'm sure you can find it. And a Twitter. We do all kinds of discussions about language changes and other things like that, or future changes on GitHub. And we have very frequent community calls where you can just join us and talk about whatever Q related. And of course, we announced all this stuff on the channels before. So thank you. And yeah, any questions? Yeah.
About how long has this been developed?
Q? Yeah. I think about 4 years now. 4 years on and off. Yeah, 4 years.
Who is using it? The companies?
I should have prepared a slide with companies that are using it. I can tell you about this. Yeah, after the talk. But yeah.
My question would be, the joke usually is if you have a configuration language, it's turning into a programming language.
Yeah, we're really trying hard not to do that. And one way we're doing that is Q is not Turing complete. It has functions, but it has no way to define functions. So all the functions that you saw were predefined in the standard library. In fact, they're more or less the Go standard library. And we have some computational aspect in Q, but we're trying to really keep it minimal and only make it easy to use for very simple use cases. So we're really trying hard to prevent people from writing like complex computation in Q itself. And the fact that we lack user-defined functions is a very big part of that. That being said, I am working right now of allowing people maybe to write their own functions, but not in Q itself, but maybe in some other language like Go or Rust or whatever they want, by compiling it to WebAssembly and basically importing it from Q as a WebAssembly module. So then you'd have access to more functionality from within Q, but you wouldn't write it in Q itself because that would be annoying. You write it in your favorite programming language, functions, computations, and then you can just call it from Q.
The question would be, I don't want to be like the Lua, for example,
Yeah.
was created many years ago as a configuration language.
Lua, you mean? Yeah.
And it's an excellent configuration language. So why would you
Well,
you're saying your major feature is less, it has less features than a scripting language?
I mean, Lua is Lua is basically a proper programming language. I mean, it's a full-on programming language. It's Turing complete. It has every feature you want.
The feature is that you have restricted.
The feature is that we have restricted features, yes. And there's also I mostly talked about the language, but actually most of the work happening in the tooling layer. We want to have modules. We want to have all kinds of things that make it very easy to use from the user side of things, which are not necessarily related to the language. Also, I don't know if I said or not, but Q is actually a superset of JSON. So it can natively just ingest JSON. And of course, if you know JSON, you already know some part of Q. So that was also, I think, a design criteria.
How do you use features? You have shown that.
Yeah, we use it. So we're using the beginning implementation in the Go standard library. So whatever that does, we just piggyback on top of it.
So basically, it's built the parser. It's like a code.
Oh, Q is written in Go. Yes, Q is written in Go. Yeah, yeah. Q is written in Go, and the Q standard library is basically more or less a subset of the Go standard library. Yeah. So the functions that now, at least now, are available in Q are more or less what you can have in pure functions in the Go standard library.
But do you envision? Sorry.
Yeah. No. It's great.
Let's say you compared it to JSON and YAML.
Yeah.
And so let's say I'm programming in Python.
Yeah.
Personally, I have programmed in Ruby script.
Yeah.
Then I can say parse JSON or parse YAML, and then in my scripting language I have the structures.
Yeah.
But somebody has to provide the JSON parser and
Yeah.
the YAML parser in
Yeah.
my scripting language.
Yeah.
So let's say I want to use Q in Ruby,
Yeah.
or I want to use Q in Python.
Yeah.
To pull in, the configuration and then
Yeah.
to do it. Like, is
this This is on the roadmap. We definitely want to be able to do exactly that from any popular language. Nowadays, it's only easily possible from Go itself, but it's absolutely a top priority to be able to make Q usable like that as a library from all the popular languages. Yeah.
Maybe one last question, if there's anyone else. Otherwise, I'm sure you can connect afterwards because you seem to have a lot of interesting questions. Thanks.
Okay.
Thanks.
Thank you.
I think we'll take as promised. We'll be back in 10 minutes, 19:38, and then we'll set up Derek in the meantime. Yeah,
Do I
that's
stop
yours.
this or
1 second, let me get mine around. Or you can actually just
I don't know what will happen with the stream if I stop
You
it.
guys are live, just so
Yes,
you're like,
not to
like
know
click
you,
the button.
how would you deal with
Okay. So yeah, hi, I'm Erik. I'm the CTO and co-founder of Domanda, which is a bookkeeping, accounting, finance management platform for small to medium companies. And yeah, we're using Go in the backend from beginning. And what I want to present to you today is my private, let's say, Go FS package. So the idea is, yeah, to have something like a unified file system within Go, so you can kind of mount zip files and S3 buckets and stuff like that, like a file system, and work with them transparently, and don't have to worry about where it came from. And yeah, so the whole thing, can see the import path and GitHub repository up top. I just looked it up. I started it in 2014, and it was kind of a toy project. I was thinking about this whole mounting, like kind of file system thing. And yeah, it just turned out that it developed into something really useful that now at Domanda we are using pretty much everywhere. So we're processing lots of files. So you import invoices and yeah, have a lot of PDFs and stuff. And internally we work on them. We change them. We pass them on from between functions and services and so on. And everywhere we have basically like, yeah, here's a bunch of bytes and it's a file. And of course, you could just pass around your bytes natively and just as bytes and your path or whatever, the file name extra. But basically, it turns out you mostly need both. You need that kind of, or you want that kind of abstraction that the file has. So it's data plus some path or a name or something. And how I started out is, of course, like usually you say, oh, I want to have like a generic file where I can access where the file comes from. And you start out, you create an interface, and then you think, yeah, you create concrete types that implement that interface for an S3 file system and a zip file system and whatever. And I started out like that, but it turned out the nicer thing to work with is just making it string based. So basically under the hood, the FS file type is just a string type. And let's see if I can show that. Yeah, I'll show it later. But basically, yeah, we have this string type that is interpreted as a path, and if it doesn't have like a URI qualifier, it's a local file path. And if you add like HTTP or S3 : / or whatever, then it's interpreted as it's coming from a different file system. And then if you register an implementation for that file system, then that can deliver that file. And yeah, so the features are, so it's really convenient to work with. You can see how and why later. Also, all the methods are cancelable by default. So using the Golang way of passing the context, a cancelable context to most functions that are long running. And it also implements file watchers, file system watchers. I haven't implemented the whole watching logic myself. I'm using the FS Notify package for that. It's also compatible to the IOFS package. So basically the authors or developers of Go had kind of the same idea. It's just the IOFS package has a much smaller scope. It's only for reading data. And my file system package can also write data. And it's also compatible with the net HTTP file system, which is another like mini file system where you can basically serve HTTP files or create a server for files pretty easily. And also if you have file with my FS package, you just call a method and you have an HTTP file system and can use that as a handler in a HTTP server. And yeah, so here are some implementations. And yeah, what does it look like? So basically, file is just a string underneath. And as I heard, not everyone is a Go pro here. So basically, in Go, you can create new types based on underlying fundamental types like string, int, and so on. And the nice thing, if you're doing that, instead of making up a more complex type like a struct, is that you can assign the basic literals for that type. So here, because it's a string, you can just assign string literals. So in Go, string literals are untyped, and you can assign it to everything that's a string underneath. And here the file is the string underneath. So yeah, and that's also the reason, because it's one of the fundamental types. You can make it const. So in Go, you can't make, for instance, a struct const. You can only make const out of yeah, integers and strings and stuff like that. And so the nice thing is you can really easily assign it, because usually if you write something, especially if you write something quickly, you just have some path that you want to pass. You don't want to call some constructor thingy. Just assign that literal. And then, yeah, so underneath, we have a very simple file system registry where some prefix is used for registering a file system. So we have the static ones like file, colon, / and HTTP and so on. And you can also use like dynamic file systems. For instance, if you open a zip file or something you have in memory, an in-memory file system, then you would have to use some yeah, unique ID and come up with your own schema on how to make that unique. It just has to be like this prefix that's used then to identify what is the file system for a path with that prefix. And yeah, here's such an example of how you can use something in memory to create a dynamic file system. So something that comes up again and again is like you have an upload dialog of some file, for instance, and you're using, of course, a multi-part form request, and yeah, want to nicely access those files, and not just access them, but just yeah, work with them like there would be normal files. And here you can see how that works. So here you just create a new multi-part FS from some form request. And the important thing is you also have to close this again, because of course it's in memory, and to free the resources, you should close that file system to free that. And you can, in that case, oops, you can still access the normal form values. If you have like an upload form where you have string values in it and some file that you upload together with that, you can still access that normally. Can you see the mouse? Yeah. But also you can access some of the form fields as files, and then basically that file has all the convenience methods, and you can pass it along everywhere and work with it like a normal file. And yeah, so here's an example of like how you can use string literals that are acceptable as FS files. So you have this read file function that takes a file, and you can just use that very convenient syntax without some new FS file blah something. You just use that string. And yeah, for instance, how you can register the HTTP file system. So it's not registered by default, but if you import the package, then it registers itself, and then you can simply, as above, you would, I must not click on this stuff. Yeah, you have the same simple syntax, and it's the same code. And basically, if you use FS file, you don't have to worry about anything. You just write this URL and it works. And also, that's a little bit confusing. So this is my own HTTP file system that just reads HTTP GET requests or converts file system reads into GET requests onto HTTP. And then, of course, there's this other HTTP file system from the net HTTP package where you can use a file or a directory as base from where you serve static files. And yeah, I mean, the file class has the methods you would expect, so they are all very convenient. You can see what you can do. You can also join paths, and it's all cleaned up and replace the tilde with the home directory and everything that you would expect that you might not always get from the standard library. Those small conveniences, they are all in there. Of course, yeah, how to access the meta information of files. It's also a little bit more convenient than the OS standard package. Also, content hashes are supported out of the box because of historical reasons. I'm using the algorithm that Dropbox is using for the content hash because we also have a Dropbox file system. And there is also the stat or info method that gives you some file info struct that you can use with the meta information, and that also has a conversion method that converts that to the IOFS file info, which is the meta information type of the FS package, which is also identical to the OS package. Yeah, it's nothing special. It just has an SHA. No, it's an SHH 256 that uses 4 megabyte blocks, something like that.
But it's a standard algorithm.
Yeah.
It's still a custom standard industry.
No, it's not an industry standard. I just started, let's say, for historical reasons with that because.
No, I mean, the Dropbox
algorithm it's nothing special. It's just a hash that works with blocks instead of one linear stream. And yeah, of course, the functions you would expect to like just give me everything as bytes or give me everything as a string, or open a reader or a read seeker that implements basically those interfaces in part from the standard library, in part like the open read writer. So there's no standard library, which is a read, write, seek, closer. So something that can do everything: read, write, seek, and close. So that's also implemented here. And yeah, so no rocket science here. It's just a little bit more convenience, most of the time to use those methods than the standard library. But the nice thing is really you can just pass it around everywhere, the FS file or FS file reader, which I'll show in a moment, and basically everything works and you don't have to worry about where the files are coming from. And so, the file reader. So what we noticed is really what's really happening a lot is you're passing around files. So you're building up some files in memory, or you're modifying them, or just read them somewhere, and you pass it to another function or some microservice or whatever. And usually you just have that file somehow readable. And how the standard library would do it is you have usually an IO reader, which gives you the possibility to kind of read bytes, but you don't have like the attached meta information, at least of a file name or maybe path or more things. And very often when working with files and not just data, but files, it's important that you know what the file name was and so on. It's more convenient to pass around a file reader instead of just an IO reader. And yeah, and the file reader has all the read methods of FS file. But here it's it's an interface, and yeah, FS file implements that. But being an interface means you can't simply assign a string literal to that anymore. So if you want to call that read file with the file reader, you first have to wrap that literal here, that string, as an FS file, because that implements that file reader. And also used a lot. I mean, it's absolutely simple, but yeah, usually you have a file and you have a bunch of bytes and the name for that, and you pass that around because you want to have that name attached to the bytes. And for that, we have the mem file, and yeah, it implements file reader and is used internally a lot. It also nicely marshals and over different APIs and so on. So yeah, here you can see how it's used. No rocket science here. And yeah, so about listing directories. So here you have this question, how do you approach that? If you have really big directories, do you want to return all the files at once at a slice, which might be like millions of files, or how do we want to do that? So this package supports two ways. One's as a callback, where you can just return some error if you don't want to continue with listing the files. There are also methods with which take a context, where you cancel the whole operation. And yeah, in general, it has all combinations you want for your convenience, how you use it. So you can use this callback like syntax here, or you can just return a slice of files. Yeah, and that's it basically for that very simple library. Yeah, as I said, it's not rocket science, but it turned out to be really useful and more convenient, I find, than the standard library. So just to fill up this presentation a little bit, I wanted to show something which is also new in Go, which is generics. And yeah, what I here implemented is a little configuration file loader. You can see the import URL, dynconfig. And the goal of the whole thing is usually for some configuration Go, you have a struct and you want to have that struct filled from like some JSON file or some Q file. And basically, what this little library does for you is, I haven't thought out that presentation very well. I just added that in the end. But basically, what you want to have here is you have this. Don't click on it. You have this configuration variable, and it has a getter method, and it on demand loads the configuration. It watches the file system for any changes. If you call get again, it just gives you always the latest version. And to make it easier to use the whole thing, it doesn't return an error. You assume that your configuration was successful, and you just always get the latest configuration. And if the file changes on disk, you just can use it. You can also check if the configuration file exists, stuff like that. But basically, how you would still get your errors if something isn't working is with this must new, or with the new function, where you can configure callbacks on what happens if it loads. Do you have to log it like here, or modify something in the configuration, or what happens if there's an error? Do you want to panic, or just fix something and return the fixed thing instead? And also what happens if the configuration invalidates and I have to reload it. So here we're just logging it. And the nice thing here is with the Go generics is basically this loader function. So this loader function injects kind of the type of the configuration into the whole thing. So you don't see any template braces here, except for here. This function is again templated function. And the type here that it uses is a string set, which is just a set of strings. And here, this example would be you just read the text file and you have a unique set of strings that are whitelisted emails that you want to accept. And that's something that I found basically when playing with generics in Go, you are solving a lot of problems with functions. This is the new function. Yeah, so for instance, here is this loader function. So one of the tricky things with the Go templates is that they are not supported on interfaces, which, yeah, it made some problems and they haven't resolved that. And basically, if you can't have them for interfaces, then a lot of other things go away, and basically you resort to moving everything to like top level functions. And for top level functions, the generics work. And here is such a loader implementation that just loads a JSON into some type, overrides then what was loaded with environment variables, if there are any, and then returns the thing. And with such a simple function, basically, yeah, you can basically create this whole machine that on demand loads your configuration, gives you the templated type, and yeah, does everything in the back, and the whole thing thread safe. And yeah, then there are, of course, the functions you would expect for different kinds of configurations. And that's also one small toy thing I did just to see what the generics or templates, it's called generics, in Go do. Yeah, so that's it basically from my presentation. At Domonda, we are hiring. We're looking for senior Go and React developers. We're growing our product and yeah, looking for people who want to join us. We're a small team, small startup based in Vienna. You can work also remotely. And yeah, if you're interested, hit me up. And yeah, here's some relevant links and packages from myself and Domonda.
Thanks. Any questions?
Yeah, so you said that the file, the underlying type is a string. I didn't quite get what's the string used for. Is it the content of the data, or is it like the...
No, so yeah, that's the thing. So the string itself is just a path or a URL or something. The nice thing also with that is if you just use that a value of that type for some marshalling, unmarshalling, printing or whatever, you always get the path, which is usually what you want to pass on. Except for GOP decode and encode, where you usually want to have some binary data there. It implements the interfaces to transfer the file name and file data.
Other questions?
In case of multi-part form, is it possible to just proxy file with a reader interface without touching disks? Is it in memory operation, or how it works?
Well, the standard library is perfectly fine for using multi-part forms. The thing here is just the convenience that you just wrap this whole request basically into a file system and can just access the files that were uploaded with that, like all other files that are FS file implementations.
Question here?
The file systems that are not backed by the standard library are in separate repositories, right? So you don't pull in Dropbox dependencies.
Yeah, right. So the different file systems, except of the local file system, which you're always using, they are in sub packages, and you are not importing or mounting kind of all kinds of file systems. So this is also the reason why, for instance, if you want to use HTTP files, you have to import, even if it's an empty import, just so you have it, then it registers itself, and then you you can use those kinds of paths.
Okay, one last question.
You said that FSFS implements IOFS from Go 1.16. Did it happen like naturally, or did you have to do something to make that work?
It's basically just wrapping because some small details of the file info type are different, but it's very thin.
Thanks again. We'll just do a technical 2-minute break and go straight into the last shortest talk for today. So, and you can enjoy the socializing afterwards. You can unplug it.
Well, yeah, I'm Klaus. I'm head of community at CrowdSec, and we're not hiring, at least not per se. But I'll talk about that in a little while. Before we start, the first thing that happened in my professional career was when I got fired. It was almost 2 years ago. I worked with one of the biggest online retailers in Denmark. And the reason why that's relevant, that's because that's the reason why I'm here today. I used to be an InfoSec professional. I've been that for almost 20 years. But I never really found my place. I never had a job where I thought, well, I love this, and I'm going to have this for the rest of my professional life. On the contrary, it became harder and harder to find anything I actually gave a flying shit about. So eventually it dawned on me that what I really loved about my job was all the things that I did in my spare time, which is the community stuff like this. I've been arranging InfoSec meetings in Copenhagen for many years, and I really love when we're having events like this, when we are together, when we're learning stuff, and we are meeting new people. And eventually it also dawned on me that could be a real job. So here I am. But the reason why I say it is also because I really hope for you guys that you are doing the job you love, and if you're not, go for it, because that truly gives you happiness. Anyway, what am I even doing here? Because I'm not even a programmer, right? Well, the thing is that CrowdSec is primarily written in Go, and it's free and open source software. And there wouldn't be a community. If there wasn't a community, there wouldn't be a CrowdSec, because first of all, it's free and open source, and also the CrowdSec is, as the name suggests, using the crowd, meaning the community, to do stuff. But I'll talk about that in a little while. Yeah, and also I'm also here because we'd also like new contributors. So we're not hiring per se because we can't exactly pay you, but we would of course we could use your code. And also we are having a bounty event in January where we first will use the weekend to write extensions, process scenarios. I'll talk a little bit later about what that is, but we'll also use the event to launch a bounty program where you can actually implement functionality and get hard cash. So maybe I'm hiring a little bit, I don't know. That's for you to decide. And also I have stickers. Yeah. Yeah, exactly. That's the spirit. All right, cool. And also before you start wondering what that llama is about, it's not a llama, it's an alpaca. And I'm sure you know this already, but alpacas are really sweet and cuddly, whereas llamas are fucking insane. Right? They'll chew your arm off and they'll spit you right in the face. So nobody in their right mind would like a llama as a mascot. So of course we are using the alpaca. CrowdSec is free and open source. It's free forever. The license we chose for it is the MIT license, because the thing about the MIT license is that once the code is open, you cannot close it again. Because we are a startup company, and while we would not mind an American company showing up and buy us for an awful lot of money, because then we'd all be millionaires, that wouldn't be a problem. But I wouldn't want them to, close everything and screw the community that has made CrowdSec what it is. We absolutely don't want that. We have a strong focus on community. I'm hired to do just that, right? So I have management and founders who knows that the community is important. So that's a big focus for us. In terms of the way it works is that you use CrowdSec to share information about the attacks you see on your services, and then mitigate the attacks, and then share the information with everyone else. And while you may think that sounds awful, and that we would want to harvest your data and all that stuff, we don't. The thing is that it's not really difficult to become GDPR compliant if you don't really collect anything, right? So the only thing we collect is actually only the IP of the attacker is a timestamp and the name of the kind of attack they're doing. Like, as I say, brute force, that's a name, and that's the only thing that's being collected and the only thing that's being shared. And it can be disabled, but then of course the whole crowd thing goes away. Because the way CrowdSec works is kind of like the Waze of cybersecurity. Waze is this GPS app that collects information about you while you're driving and shares the information with everyone else, so that the others will know what to do, so they don't end up in that awful long queue that you're ending in. So, or that you spend the last hour in. So that's, yeah. And as I said, CrowdSec does the same thing with sharing the information about the attacks that it sees, because it's the way we thought, or rather the whole idea about CrowdSec is that there's a lot of cyber criminals out there, and whatever happens, it seems like they are getting more and more success. And we've tried a lot of things. We've tried, giving security a lot of money, and yet it really doesn't matter because people are still getting breached. They're still getting ransomware. So instead, we want to try a new approach, like outnumbering the bad guys. Because if you think of it, it kind of makes sense, because we are more law-abiding citizens than we are bad guys out there. So why don't we stand together, work together to fight against cyber criminals? That's the whole point. The way CrowdSec works is that CrowdSec reads your log, right? So CrowdSec has a number of data sources like syslog. It spins up a syslog server. It can, if that's what you want. Journal-D, AWS CloudTrail, Kinesis, Docker log, Windows event log, and just a normal file that's also supported. CrowdSec detects threats in your log files and mitigates those threats. Then it sends signals back to our cloud, whatever you want to call it, our cloud. And we have a mechanism, you would call it like a back office mechanism called the consensus engine that tries to figure out which of these are actually real bad guys. It does so by correlating attacks or correlating information across agents to see, well, who of those are really bad. And then it shares that as block lists to all agents and fully automated. CrowdSec can detect like a number of different attacks. CrowdSec was really, to begin with, CrowdSec was inspired by an open source project called Fail2Ban, which is a fantastic 20-year-old tool made by a guy who wanted to learn Python. And obviously that, as I said, is a very, very good tool, but it's 20 years ago, and Python, you know, as you of course know, Python is not near as effective or, you know, memory resource optimized as and fast, of course, as Go. So Go is a much better choice. CrowdSec can handle the same attacks as Fail2Ban, but it's more complex. You can do more things. It can detect like credit card stuffing, voice over IP abuse, bot scraping, monitoring, layer 7 DDoS, port scans. Basically, CrowdSec is a rule-based engine that can detect any kind of deviation. No AI, ML, fancy stuff, nothing like that. Protecting an application takes three things. It takes a data source. You won't normally use those. You would normally write one of those, although that is part of the bounty program that we are launching in January. Then it would need like a parser file. It's a simple file written in YAML, and it has a simple line, some lines of grok that basically tells you tells CrowdSec how the log file looks like, right? And then there's a scenario that describes the attack. For instance, on the SSH brute force, it describes how many logins on how much time do we accept before we think it's a brute force attack. And creating those parser scenarios in general, that's pretty trivial. CrowdSec is API driven. Everything in CrowdSec speaks together using REST API. So the way data flows in CrowdSec is on the left side, data comes in, then behavior is being detected by the agent in the middle, and the local API, the CLI version of CrowdSec or CLI. CrowdSec CLI is speaking to the local agent using API. The CrowdSec agent pushes signals back to our central cloud thingy, and the bouncer, which is the IPS part of CrowdSec, query the CrowdSec agent over REST API to find out which IP should it mitigate or block. It also supports notifications, also API. CrowdSec is ops friendly, observability, infrastructure as code. DevOps friendly, Helm chart for Kubernetes, serverless, AWS is heavily supported since we run everything in AWS ourselves, and it's very portable in part thanks to Go. CrowdSec runs on Linux because, in the end of the day, we are mere Linux nerds, right? So CrowdSec supports most distros, and those that we don't support, the community supports. So Arch is supported not by us but by the community, but we support Debian, RPM, E, and all those. Well, I'm a Debian guy, so I just know that Debian is supported, and that's really all I care about. Both x64 and ARM and OpenWRT and Synology. Windows is fine. It was released a couple of months ago. It's not as feature rich as the Linux version, but that's more the Windows stack in terms of, like, for instance, I'll talk a little bit later about which programming languages or that CrowdSec hooks into. We don't hook into C# because nobody in the company knows anything about C# or .NET. So yeah. Anyway, FreeBSD, OpenSense, Helm charts, Docker, and Kubernetes, of course. In terms of bouncing, the mitigation part, CrowdSec supports AWS WAF, Cloudflare, Fastly. On provider level, on network level, there's a bouncer for host firewalls on the OS that we support. That means IP tables, NF tables, PF, and Windows firewall. And also, in terms of BGP, we are working on supporting BDP and working with a provider of BDP blog lists, because one of the whole ideas about CrowdSec is that we want to cut off the bad guys by the root, and if we can set up a global network that's detecting those attacks by right away and then blocking them on BDP level, so that and in case you don't know it, BDP is a protocol used for inter-ISP communication. So we can null route the IPs, as I said, on a very low internet level. That would be really, really cool. In terms of servers, Nginx, traffic, Caddy, HA proxy, and a bunch more, and also PHP, Python, JS, and Go. Well, basically what that means is about one line of code you can include CrowdSec support, in the sense that there is a bouncing mechanism right inside your application. So that's pretty cool. Yeah, that was it. We have a friendly Discord community where we have workshops. We're on Twitter. I'm on mail, and I'll be in Vienna until Sunday. So yeah, send me a mail or get in touch, whatever you want, if you have questions, of course.
Thanks.
Yeah. I almost did it on 5-10 minutes, but yeah. Well.
Perfect.
Yeah. All right. Cool.
Questions?
In terms of the rules you're evaluating, like, are they like the ModSec or real set, or like what type of attacks are you detecting?
It could be literally anything, because in terms of ModSec, CrowdSec supports reading ModSec logs. So whenever an attack is detected by CrowdSec, it blocks that and makes it, crowd aware, in the sense that if you have CrowdSec in your perimeter firewalls, and one of your firewalls or one of your web servers has ModSec installed and it detects an attack, it will it will detect the attack and then make all the other firewalls block that stuff right away. So it's this good old-fashioned Unix way of thinking, that you don't want to implement things that works fine. You want to improve things that already exist. Yes?
What's the time to live of one rule? Because I'm thinking about floating IPs and just grabbing an IP of a bad guy after you use it for attacks.
The IPs in a blog list are only there for 72 hours. Then they, if they're not refreshed, then they run out, because the internet is volatile, right?
Yeah.
Yeah, because one thing that we found out once we started collecting data on at scale is that we know, or we can get indications when an IP is getting compromised and when it's stopped being compromised. And since we know which IP it is, we also know which ASN, which support or which provider it is. So we can start getting an overview per ASN on how good cloud providers, for instance, are at cleaning up after the bad guys. So last year, or in the beginning of this year, we did a little survey around it where we found out that AWS on average had a malevolent duration, as we call it, for 3 days, whereas OVH, another cloud provider, has an average malevolent duration of 17 days. So providers are different, and also 80% of the IPs on our blog lists are IPs that has been there since day one. So we also have a ton of providers who don't give a shit, right? Yes.
Someone who isn't deeply into that stuff, what kind of signals or types of signals are you looking for?
The kind of signals we send, because we collect data about the attacks, and then we send those as signals, right? And
what signals that it's in a
that, for instance, it's an attack. Okay, it's a malicious IP address or something, and then is it the pattern on the timing on how they request stuff, or what path?
Yeah, well, that is in the part of that is in the scenario. For instance, Z brute force is apparently the only example I can think of, and there it looks for how many attacks, how many logins from the same IP in how long time does it take before we think it's a brute force attack. And similar for if you have a ticket selling site and you want CrowdSec to catch all the bot scalping things, and bot scalping is when a bot buys up things on your website to sell them off at a higher price, right? CrowdSec can see that, for instance, that how many connections is one client doing, and if one client is making more than 2 or 3 connections per IP, then something is off, and we're cutting it off. So it depends very much about what we're looking for in the scenario, but that is, as I said, that's totally flexible because it's YAML, and everything that we can look for, and that is also able to put in a scenario file or available for a scenario file.
One last question? Maybe, yeah.
Fail to ban has lots of filters, as I understand. CrowdSec also has a lot of them by default.
Yeah, yes, but fail to ban has 20 years of people writing filters, and we've only had 2. So.
But then, how easy is it to create new filters and test them?
Really, really easy. I mean, it's a matter of writing a grok pattern and then understanding how the YAML structure works for the parser, and then the same thing for the scenario. There is some documentation on our website, which is honestly not the best because, yeah, there is an example, but it's very simple. I'm working on writing on a workshop where we do that stuff, because obviously the more log files and services are supported, the better it is for us. So also for this bounty event we are doing in January, we want people to write parsers and scenarios that detects commonly known exploits. Whenever an exploit is being used, or so whenever a vulnerability is being exploited, you can oftentimes tell in the log, and that detection part we want, and also the scenario part, or sorry, the detection part we want people to write. And before we start this entire weekend of bounty thing, we are making we're doing a workshop where we teach people what is a scenario and parser and how do you do it. But it takes a couple of hours if you know what you're doing.
Thanks. Dan, thanks again.
Thanks.
Dan, thanks a lot for watching. If you did, or watching the recording, we get some echo live. Awesome. And big wave from everyone here. Take care. Ciao, ciao.